Why does a droplet suddenly levitate and dance when it touches a scorching hot surface? That's the mesmerizing phenomenon known as the Leidenfrost effect, where liquid droplets appear to hover and skate across hot surfaces, never boiling away immediately. When a surface is far hotter than the liquid's boiling point, the bottom of the droplet vaporizes instantly, creating a thin cushion of gas that lifts the droplet up. This vapor layer acts like a levitating airbed, reducing contact with the hot surface and dramatically slowing down evaporation. The result? A droplet that glides, spins, and bounces like it's alive. But why doesn't it just explode into steam? The key is that the vapor layer insulates the droplet, keeping it from direct contact with the heat source. This counterintuitive behavior defies the expectation that more heat means faster boiling, because in this case, more heat actually slows the process down. The droplet's motion becomes even stranger on textured surfaces where it can climb slopes, spin in circles, or even self-propel in one direction. It reveals that complex motion and stability can emerge from simple thermal physics and turns an everyday event, boiling, into a stage for dynamic, gravity-defying behavior. How can a simple water droplet dropped onto a pan hotter than 200 DGC refuse to boil away and instead skate and vibrate like a miniature hovercraft? This is the Leidenfrost effect. Once the surface exceeds a critical temperature, a vapor cushion forms beneath the droplet, insulating it and letting it levitate and dance instead of evaporating instantly. When the surface temperature climbs above the Leidenfrost point, liquid at the interface vaporizes so rapidly that a thin vapor layer lifts the droplet. What keeps the droplet from collapsing? That vapor cushion sustains a delicate pressure balance. The weight of the droplet is matched by the upward thrust of its own escaping steam. Friction drops to nearly zero, so even tiny asymmetries in the vapor flow send the droplet skittering across the surface. Why does the droplet dance instead of drifting randomly? Surface imperfections and temperature gradients break the vapor flow symmetry. On a perfectly smooth, uniformly hot surface, droplets can spin in place or trace circular paths. Introduce a slight slope or texture and they zip along rails of hottest regions, oscillate back and forth, or trace intricate racetracks. It's the interplay of vapor pressure and Marangoni flow's surface tension variations driven by tiny temperature differences that choreograph the motion. Beneath the dancing lies a world of fine-scale physics. The vapor film is only tens of microns thick, yet supports droplets a few millimeters across. Its thickness and stability depend on droplet size, liquid properties, and surface emissivity. Too small a droplet and heat leaks through, collapsing the cushion and causing a sudden boil-off. Too large and the vapor can't escape fast enough, leading to erratic bouncing or break. Can we control the dance? Absolutely. Engineers craft surfaces with patterns, grooves, or varying wettability to steer Leidenfrost droplets like magnetic marbles. By tuning surface temperature and texture, one can sort droplets by size, mix tiny volumes without contact, or harvest energy from their motion. The very mechanism that seems magical is now a tool for microfluidics and heat management. In essence, Leidenfrost droplet dancing isn't just a kitchen curiosity, it's a vivid demonstration of how extreme conditions, here, blistering heat, can spawn surprising stability and motion. It reminds us that, under the right circumstances, a destructive force can spawn a self-insulating, self-propelling system, pushing the boundaries of our everyday intuition. When a liquid drop contacts a surface significantly hotter than its boiling point, it creates a thin vapor layer that insulates and lifts the droplet, causing it to levitate. This phenomenon, known as the Leidenfrost effect, reduces friction and heat transfer so the drop skitters across the surface rather than boiling away immediately. Small asymmetries in the vapor film or surface texture can induce spontaneous motion and oscillations, making the droplet dance. The interplay of vapor generation, surface tension, and thermal gradients drives this self-propelled behavior. On a hot griddle at 280 degrees Celsius, water droplets skid around for seconds, spinning and bouncing before evaporating. It is like a puck gliding frictionlessly on an air hockey table, propelled by tiny jets of air from below. At moderately high temperatures, liquids undergo nucleate boiling, forming bubbles that detach and rise, keeping the drop anchored to the surface. Once surface temperature exceeds the Leidenfrost point, typically 1.5 to twice the liquid's boiling temperature, the vapor layer becomes continuous and stable. In this regime, the drop no longer makes direct contact, radically altering heat transfer and flow dynamics. Thus, the Leidenfrost regime represents a distinct phase where vapor lubrication dominates. Ethanol boils vigorously at 87 degrees Celsius, but levitates only above around 190 degrees. It is like switching from walking through a jungle to floating on a river of mist. Leidenfrost. As the hot surface rapidly vaporizes the liquid at the contact interface, a high-pressure vapor cushion forms beneath the droplet. This cushion balances the droplet's weight, preventing wetting and minimizing direct conductive heat transfer. Molecules evaporate continuously at the interface and rush outward, supporting and propelling the drop. The thickness and stability of this cushion depend on surface temperature, liquid properties, and droplet size. High-speed imaging shows a vapor pocket of tens of micrometers forming under millimeter-scale water droplets on a heated metal plate. It is like a hovercraft that rides on a cushion of its own exhaust, barely touching the ground. Temperature gradients along the vapor-liquid interface create variations in surface tension, driving fluid from low-tension regions to high-tension cooler areas. These Marangoni flows within the droplet generate circulation patterns that can propel or spin the drop. Coupled with the vapor thrust beneath, these internal flows produce complex trajectories and oscillatory motions. The competition between vapor pressure forces and thermocapillary stresses shapes the dancing patterns. Silica nanofluid droplets display vivid spinning when surface tension gradients induce rapid internal circulation. Under Leidenfrost conditions, it is like stirring honey by heating one side of the spoon. The syrup flows toward the cooler side, creating a swirl. Micro and nanoscale patterns on the surface can break the symmetry of the vapor film, channeling vapor jets in preferred directions. Ratchet-shaped surfaces, for instance, drive droplets unidirectionally by guiding vapor escape beneath the drop. Even random roughness can induce erratic dancing as the droplet repeatedly pins and releases on asperities. Engineering surface geometry thus provides a route to control droplet motion without external forces. On a sawtooth pedal-plated Leidenfrost drops thermally walk uphill along the ratchet direction. It is like skateboarding on a half-pipe whose shape funnels your motion along a specific path. Leidenfrost droplets can undergo shape oscillations, spheroidal modes that resonate when the vapor emission frequency matches the droplet's natural frequency. These resonances amplify droplet deformation, leading to rhythmic, bouncing, or star-shaped oscillations. Such nonlinear behaviors depend sensitively on drop size, temperature, and fluid properties. In some cases, coupling between translational motion and shape oscillation produces intricate dancing trajectories. Alcohol droplets at the Leidenfrost threshold exhibit star-shaped standing wave patterns oscillating at tens of hertz. It is like a juggler keeping a balloon aloft by tapping it at just the right rhythm to match its bounce frequency. The insulating vapor film drastically reduces heat flux compared to nucleate boiling, posing challenges for cooling technologies that rely on efficient phase change. Conversely, harnessing Leidenfrost mobility enables frictionless transport of tiny liquid volumes in lab-on-a-chip devices. Controlled droplet racing, mixing, or sorting on heated patterned surfaces becomes feasible without pumps or electrodes. Understanding and manipulating droplet dancing thus opens new possibilities in microfluidic actuation and thermal management. Researchers use heated ratchet plates to shuttle picoliter droplets for biochemical assays without mechanical contact. It is like using conveyor belts of hot air to move objects across a factory floor without any physical rollers or tracks. Accurately simulating Leidenfrost dynamics demands coupling vapor generation, thin film hydrodynamics, heat transfer, and thermocapillary effects. A formidable multi-phase problem. Experimentally, maintaining uniform surface temperature and avoiding contamination or oxidation is critical for reproducible droplet behavior. High-speed imaging and microfabrication techniques help unravel the phenomena but cannot always capture subsurface vapor flows. Bridging these modeling and experimental gaps is essential for predictive control. Computational fluid dynamics models often struggle to resolve the nanometer scale vapor layer beneath a dancing droplet due to mesh resolution limits. It is like trying to photograph a hummingbird's wingtips with a slow shutter. You need specialized tools to freeze the motion and reveal the details. Advances in surface engineering, such as programmable wettability and tunable heat flux, promise dynamic control of Leidenfrost behavior, enabling on-demand droplet routing and mixing. Exploring different liquids and environmental pressures may extend droplet levitation to new materials and temperature ranges. Insights gained here could inform the design of frictionless bearings, self-cleaning surfaces, and compact cooling systems for electronics. Ultimately, mastering the dance of Leidenfrost droplets could revolutionize fluid handling in harsh or miniaturized settings. Engineers are developing electronic cooling plates that exploit localized Leidenfrost regimes to shuttle coolant droplets across hot spots. It is like choreographing a ballet of droplets on a hot stage, each performer moving precisely where and when needed without any wires or magnets.